Okay, let's take a look at a couple of problems here. Number 12. A beam of electrons enters a pair of crossed electric and magnetic fields in which the electric field strength is 3 times 10 to the 4 volt per meter and the magnetic flux density is 1 times 10 to the minus 12 Tesla, or minus 2 Tesla. If the beam is not deflected from its path by the fields, what must be the speed of the electrons? First, let's figure out what the electric field must be. Now, we have the north-south for the magnet here, so we know that that magnetic field is pointed this way, from north to south. And if a particle comes in there, we could use the right-hand rule to figure out in what direction the magnetic field would make this electron move. Now, it's an electron, so when we apply the right-hand rule here for the current, that would be for a positive particle. So we'd have to kind of use our right-hand rule backwards as far as the thumb is pointed. So our thumb should point in the direction that the negative particle came from. Our fingers should point in the direction of the magnetic field, and then your palm will point in the direction that the particle will get pushed, in which case that will be in a downward direction. So the path of the particle would come into the field, and the magnetic field would make it want to curve downward like that. Now, the electric field, which is the red lines, are going to counter that. So in order for that to happen, so that the path can be straight, we're going to have the field point in a direction that makes it want the electron go up. So the top part here is going to have to be the plus, and the bottom part will have to be the minus. And the electron will then want to move toward the positive plate. And if these two forces, the magnetic force and the electric force, are exactly equal, then the electron can come flying straight through. All right, that's what has to happen. All right, now we need a couple of equations. For the electric field, the force is going to be equal to Q times the electric field. Force will be equal to Q times the electric field. Now we're talking about an electron, so Q is going to be 1.6 times 10 to the minus 19 coulombs. Our electric field they give us is 3 times 10 to the 4, and that's volts per meter. So we can figure out the force that the electron experiences. All right, the other force then will be from the magnetic field. That force FB or FM is going to be Q times V times B times the sine of the angle between the path and the field. And if this electron is going perpendicular to the magnetic field, which it looks like it is, then the sine of 90 degrees is 1, so that part can just kind of drop out. So these two forces are going to have to equal to each other. So we could then write F from the magnetic field must equal the F from the electric field. And that's going to be Q times E, and that's going to be QVB equals Q times E. Now, notice in this case that because Q is on both sides, that's really just going to cancel out. So the charge of it's not really going to play into it. All right, the charge of it won't really play into it. And what we're trying to find here, of course, then, is just V. Just V, which would be B, E divided by B. Right? So the electric field divided by the magnetic field will be the velocity. And we're set then to put that in. 3 times 10 to the 4 divided by B, which they give us as 1 times 10 to the negative 2, And this will equal 3 times 10 to the 6 meters per second. So the electron will have to be going just the right speed in order for this to happen. If the electron is going faster than this velocity, then the magnetic force would be greater and it will curve down. If the velocity is slower than this, then the electric force will be greater and the particle will move up. But at this very specific speed, the two forces will cancel each other out. Okay, problem number 13. An electron in one of the electron guns of a television picture tube, old school television that is accelerated by a potential difference of 1.2 10 to the 4 volts. It is then deflected by a magnetic field 6 times 10 to the minus 4 Tesla. Determine the velocity when it enters the field. Now, here's what's happening. We got these two electrodes that are purpose is to accelerate the electron, and they're connected to a potential difference of 1 times 10 to the 4 volts. So the electron then leaves one and accelerates through this electric field created by this thing. And remember that a volt is equal to a joule per coulomb. All right, joule per coulomb, that's what a volt is. So just from that voltage, and we know that an electron has a charge of 1.6 times 10 to the minus 19 coulombs, we can figure out how many joules that is. So the joules of energy would be V times Q, Q times V, Q times V or V times Q. And then that is going to give the electron some kinetic energy. All right, some kinetic energy. And that's given by 1/2 mv squared. 1/2 mv squared. So the fact that the electron is accelerated by a potential of 1.2 times 10 to the 4 volts, we can figure out how many joules of kinetic energy that it has. Now be careful, because this V in this equation is for volts, and V in the other one is, or this is for velocity, and the other V is for volts. All right, so that's how much energy the electron is going to have. All right, so solving that for V, we're going to have 2 times V times Q divided by m, and that's velocity squared. Velocity squared. All right, so we can figure out what that is. Now we need to know what the mass of an electron is. The mass of an electron, and we might have to look that up if you forget what that is, but that's 9.11 times 10 to the minus 31 kilograms. All right, so V squared is going to be equal to 2 times the voltage, 2 times the voltage, times the charge, divided by the mass, and that will give us the velocity of the electron. All right, let me punch that in. That will give us 6.5 times 10 to the 7 meters per second. All right, that's pretty fast, almost getting to relativistic speeds. But that'll be how fast the electron is moving when accelerated through those two electrodes. And then it enters a magnetic field and is curved. It'll follow a curved path and curve up and then exit the magnetic fields and hit the screen. So now we want to figure out what the radius is of that curve. All right, this is a centripetal acceleration problem. Centripetal acceleration. The force from the magnetic field will be given by Q, V, B, sine of the angle between them. Now the path of the magnetic field is from these two coils here, so the magnetic field is going to be either straight up or down. The path of the electron is perpendicular to it, so our angle is 90 degrees, so we'll skip the sine thing because that'll be 1. So that'll be the force from the magnetic field, and we can use the velocity we just figured out to figure out what that is. Now what we're looking for is the radius of the curve, and the curve is going to be part of a circle, so we're going to have centripetal acceleration, which is v squared over r. All right, the centripetal force. And again, we're going to need to use the mass of the electron here, and we want to solve this for r. So these two forces are going to equal to each other, so QVB is going to equal m times v squared over r. We want to solve for r. So r will, that's going to be m v squared divided by q divided by v divided by b. All right, let me double check here. Yes. So that's the equation for r. V shown up here is squared on the top and on the bottom, so one of those v's can cancel out and get rid of that. So the mass of the electron, 9.11 times 10 to the minus 31. The velocity, which we've just figured out, 6.5 times 10 to the 7. Divided by the charge of the electron, 1.6 10 to the minus 19. And the strength of the field given as 6 times 10 to the negative 4. All right, let's punch that in, see what we get. R equals 0.62 meters. 0.62 meters. All right, which is kind of small, 62 centimeters. All right, that would be it. That will be the radius of that little curvature. Now, the electron's flying in like this, and then it goes through a curved path and exits the magnetic field and then is pointed up toward the screen. So the circle that we're talking about, just this part of it, is that radius right there, that curved part of the radius. All right, there we go. There's a couple problems.